Hello everyone, and thank you for joining us for this webinar. The webinar today will cover modeling, simulation, and analysis of battery energy storage systems. So let's go ahead and get started. Our agenda today will include some of the challenges and opportunities that define the need for battery energy storage systems. What do typical BESS architectures look like? What is a battery management system? How do you model BESS and BMS in ETAP? And what are the various applications for renewable, railway systems, as well as transmission and distribution? Let's take a look at the situation and challenges facing the electrical industry today and why energy storage systems are relevant and important. Change to energy generation and consumption is being driven by three powerful trends: decarbonization, digitization, and decentralization. Decarbonization of the world's electricity network is happening through the introduction of more renewable energy sources or higher penetration of renewable energy, driving the need for decentralization due to these affordable distributed power technologies. Consumers are therefore becoming active power producers who demand clean, reliable, and affordable power. And finally, digitization implies the emergence of digital technologies. We're also seeing that businesses must, of course, continue, and emergency security services must have uninterruptible power. Therefore, there's a need or creative need to maximize each electron flowing through the electrical infrastructure. Let's take a look at decarbonization in a little bit more detail. The rapid deployment of low carbon technologies such as wind and solar is making it increasingly difficult to forecast variable generation. Therefore, it's creating challenges around grid stability, congestion, and market volatility. When it comes to digitization, what we're seeing is more connected devices and smart sensors that are allowing fast decision making on dynamic and nodal prices, for example. And intelligent control systems and internet-enabled software are able to optimize power plants and grids, allowing for faster computational systems being able to be utilized in controlling the grid stability as well as security. And finally, decentralization is being driven through the distributed energy resources being deployed throughout the electrical system. The growing penetration of DERs, including renewables, is creating more prosumers and increasing distribution grid complexity. Regulatory uncertainties are also affecting the ability to decentralize the systems, and there's also a significant impact on performance and safety when it comes to grid decentralization. So what is our solution? Battery energy storage system is an obvious solution that applies to multiple sectors. A battery energy storage solution offers new application flexibility and unlocks new business value across the energy value chain, from conventional power generation, transmission, distribution, renewable power, to industrial and commercial sectors. Energy storage, particularly battery energy storage, is part of the answer to those challenges and a key part of the standard power supply solutions of the future. Let's take a look at some of the applications and benefits of battery energy storage systems. You can improve integration and enhance utilization of energy generated from photovoltaics or PV systems and wind turbines using battery energy storage. Through distributed microgrids, you can monetize assets through new revenue streams, increase asset utilization, improve yield, and reduce operating costs. And you can also improve safety by reducing fault current by up to 5 times. This happens due to the utilization of our electronic devices that allow for lower fault current contribution to the rest of the electrical grid. Some of the other applications include renewable smoothing. As you can see from the orange line, we can have intermittent PV production throughout the day. However, by including energy storage systems and filling the gaps, which are shown in blue, we're able to produce a smooth generation of renewable energy throughout the day. Another application or benefit of energy storage system is the ability to handle ramps or the frequently known duck curve. The ramp or the duck curve is when the energy consumption increases dramatically at a predefined time. Every country and city has somewhat of a duck curve, and the ability to handle the load ramp cannot be done through traditional conventional generators, but it can be handled very quickly through energy storage devices. Energy storage also supports diverse applications, including firming renewable production, stabilizing the electrical grid, controlling energy flow, optimizing asset operation, and creating new revenue. Commercial and industrial end users can mitigate demand charges, optimize differential or time of day energy prices, and benefit from additional on-site PV generation through the utilization of battery energy storage systems. Some of the other applications include seasonal storage, such as the ability to store energy for a longer period of time, energy arbitrage, and ancillary services where power exchange can be done through energy markets, frequency regulation and stability control by maintaining constant frequency as much as possible throughout the network, load following capability that allows for system fluctuations to be managed, power quality and voltage control where we can maintain constant voltage through reactive power injection as much as possible, black start capability where energy supply is done during grid failure and black start generators are not available or not possible to be utilized, transmission and distribution congestion relief where the energy supply and demand is served locally, investment deferral for T&D infrastructure, load leveling and peak shaving where demand is shifted and the peaks are actually reduced, off-grid support where standalone energy systems are used with off-grid networks or standalone microgrid systems, the ability to improve the renewable energy penetration, the ability for electric vehicles to act as energy sources, the ability for the network performance to be improved by correcting any unbalance in the system, and finally reliability enhancement by improving network quality of service. When we talk about battery technologies, we normally consider lead acid and lithium ion. We're all familiar with the traditional lead acid battery in a black case or the lead acid batteries that are typically used inside substations. So here's a quick comparison table between lithium iron phosphate and lead acid AGM or absorbent glass mat, also known as gel or flooded batteries. So a few features that we are comparing where both technologies have their benefits. However, the lithium-ion battery prevails on these primary features. It is typically considered wise to use just 30 to 50% of the rated capacity of lead acid deep cycle batteries. This means that a 600 amp hour battery bank in practice only provides at best 300 amp hours of real capacity. Even if you're going easy on your batteries and are careful to never overly drain them, even the best deep cycle lead acid batteries are typically only good for 500 to 1,000 cycles. If you're frequently tapping into your battery bank and utilizing batteries, this could mean that your batteries may need replacement after less than 2 years of use. The final 20% of the lead acid battery capacity cannot be fast charged. The first 80% is usually bulk charged by a smart multi-stage charger, but then the absorption phase begins and the charging current drops off dramatically, making the last 20% a slow charge process or a trickle charge process. Lead acid batteries suffer yet another inefficiency issue that they waste as much as 15% of the energy you put into them due to the inherent charging inefficiencies. So if you provide 100 amps of power into a lead acid battery, you're actually only storing 85 amp hours effectively. The faster you discharge a lead acid battery of any type, the less energy you can get out of it. This is also known as Paukert's loss, and there is essentially Paukert's law named after the German scientist W. Paukert, which says that in practice, high current loads like air conditioners, microwaves, induction cooktops, they can result in lead acid battery being able to actually deliver as little as 60% of its normal capacity. This is a huge loss in capacity when you need it the most. Related to the loss is also the voltage sag that is experienced when the battery is applied to a large current load. And finally, on the dimensions, we can see the size, weight, and the current density of the lead acid battery is large, heavier, and lower current density as compared to a lithium-ion battery of similar capacity. So when we apply a lithium-ion battery in a battery energy storage system, this is a typical or traditional BESS architecture. It consists of the lithium-ion battery connected through a battery management system or BMS that is able to transfer power to the power grid through converter electronics. The converter electronics is essentially bidirectional, allowing the battery to charge and discharge through the BMS using supervisory control. The supervisory control can be communicated through ICT infrastructure to a microgrid controller or to a SCADA system, or the BMS may have its own local supervisory control that makes decisions on when to charge and discharge the battery based on the state of the power grid. The battery management system also allows for data acquisition, so it allows the SCADA or external system to gain knowledge about the health of the battery, such as the state of charge. What is state of charge or SOC? We can see it with a simple diagram here. We normally look at our favorite smartphone and we see our battery symbol, which goes from 0 to 100%. Behind the scenes, the battery is being charged using a charging current, shown in the blue line, and it's usually constant current charge up to a certain state of charge, after which the constant current changes to a decaying exponential value. Correspondingly, the battery voltage rises as the charging current is applied, and it remains fairly constant voltage till the charging current starts reducing after reaching a preordained state of charge, and the battery voltage starts climbing and becomes constant, which is where we have reached 100% state of charge and the battery is ready to take on some load in the system. So let's see what happens to the battery state of charge and the concept of current rate or C rate. As the C rate is varied, you can see that the open circuit voltage is varied upwards and downwards. So the voltage either increases or decreases based on C rate, and the discharge profile varies accordingly. As the battery is being discharged, we can see that the discharge point represented by the black dot follows the discharge curve till the battery voltage goes to a minimum value. And as the battery is charged, the black dot essentially moves up and arrives at the open circuit voltage of the battery cell. In reality, the charge and discharge curves are not the same, but we will look at those details later. What is C rate? C rate is a measure of the rate at which a battery is being charged or discharged. It is defined as the current through the battery divided by the theoretical current draw under which the battery would deliver its nominal rated capacity in 1 hour. Or simply put, C rate is used as a rating on batteries to indicate the maximum current that the battery can safely deliver on a circuit. Standards for rechargeable batteries generally rate the capacity over a 4-hour, 8-hour, or longer discharge time. Special purpose batteries such as computer UPS may be rated by manufacturers for discharge periods less than 1 hour. Because of internal resistance loss and the chemical processes inside the cells, a battery rarely delivers nameplate rated capacity in only 1 hour. Another way of looking at C rate is through an example. When a 100 kilowatt battery in a Tesla Model S P100D electric vehicle is undergoing supercharging at 120 kilowatt, the C rate is 1.2 per hour. And when that battery delivers its maximum power of 451 kilowatt, its C rate is 4.51 per hour. So we see that the battery management system gives us the ability to monitor state of charge. But the BMS is more than that. It may monitor the state of the battery as represented by various additional items such as voltage, and that could be total voltage, voltages of individual cells, minimum and maximum cell voltage, or voltage of the periodic taps inside the battery, as well as current, which is flowing in or out of the battery. The BMS can also monitor temperature such as average temperature, coolant intake temperature, coolant output temperature, or the temperature of individual cells. It can monitor the state of charge or depth of discharge, DOD, to indicate the charge level of the battery. It can also monitor state of health, which is a measurement of the remaining capacity of the battery as the percentage of the original capacity. It can also monitor state of power or SOP, the amount of power that is available for a defined time interval given the current power usage, temperature, and other conditions. Also, state of safety, aptly known as SOS, as well as coolant flow for air or fluid cooled batteries. In ETAP, battery energy storage systems are utilized all the way from design to operations. Now that we've seen some of the basic terminology of BESS, BMS, we can see that inside ETAP, the applications for battery energy storage system are obviously for optimal charging, discharging, and arbitrage calculations. And those computations can be used to improve efficiency and support grid modernization. The BESS implementation in ETAP is an integral component of ETAP microgrid controller, as well as an integral component of ETAP DERMS, or Distributed Energy Resource Management Systems. We can use intelligent battery parameter estimation inside the ETAP BESS implementation. It can be used for behind and front of the meter applications. And you can use the BESS modeling and simulation in ETAP for frequency, voltage, ramp, and other demand response simulations. And finally, it also includes the implementation of battery management system, or BMS. Before we get to the program, let's take a look at some of the modeling challenges and the need for some of these capabilities. So one of the modeling challenges for battery energy storage is the complex nonlinear behavior of the charge and discharge curves. And as we have seen earlier, the various C rates that may be possible and provided by the battery manufacturer that follow different charge and discharge profiles. And as we can see, the charging and the discharging curves do not follow the same path. There is an hysteresis that is typically applicable that depends upon the chemistry of the battery, allowing or preventing the charging and discharging to not follow the exact same path. Other modeling challenges include the wide range of operation, so you can vary the battery from 0 to 100% state of charge and get different results. There's a wide range of battery sizes going all the way from 2 to 100 amp hours or more. There's a wide range of battery charge and discharge currents that can be used, as we've seen, from 0.1 to 10 C, or current rate. The constant current and constant voltage and user-defined charging profiles can be variable. And the battery itself is a load as well as a source, allowing for bidirectional power flow and requires modeling of the associated power electronics. When we look at the mathematical modeling inside ETAP, we essentially use the manufacturer data sheet to begin with, and we prepare a parametric model of the battery. This parametric model utilizes various parameters provided by the manufacturer to estimate the charge and discharge characteristics of the battery. State-of-the-art intelligent optimization methods are used to convert the manufacturer data sheet and the parameters into optimized parameters and the corresponding charge and discharge curves that will be utilized during the simulation. Therefore, in ETAP, you can actually develop a battery inside the battery library and use battery parameter estimation to estimate the charge and discharge curves if they are not provided by the manufacturer. If they are provided by the manufacturer, you can also use parameter estimation to compare the manufacturer as well as the estimated curves. So let's take a look at the parameter estimation in action. We can access the battery library that gives us the ability to select between two different battery technologies, as we have looked at earlier: lead acid, lithium ion. Whenever you select any of these battery technologies, you can then utilize the battery parameter estimation to plug in the battery parameters based on the nature or the chemical composition of the battery, and then utilize parameter estimation to calculate the discharge and the charge characteristics of the batteries. This battery parameter estimation works for lead acid as well as lithium-ion batteries. Looking at the parameters for the lithium-ion battery, the program allows you to essentially define standard values that recomputes the standard curve versus the previously estimated curve. You can then also change the exponential portion of the charge and discharge characteristics, and in near real time observe the change in these variables as it affects the charge and discharge characteristics and the profile of the battery. Once you're happy with the profile that you have created, you can then go ahead and start utilizing this particular battery that has estimated parameters along with various simulations within ETAP. Let's look at a very simple system and observe how DC load flow and DC analysis is carried out using the new lithium-ion battery. In this particular system, we have a battery delivering power to a DC network and an AC charger, which is a bidirectional charger or rectifier that is able to supply power to the AC side or absorb power from the AC network as well. We also have included a solar panel to essentially provide an alternative source of power. You can simply open up the battery editor by double-clicking on the battery element, and once you go to the rating page, you can essentially see a definition of various state of charges. This is similar to the loading and generation category in ETAP for generators as well as loads. Of course, for the battery, we have also defined the number of cells, number of packs, and number of strings. The rated open circuit voltage is essentially nothing but the volts per cell times the number of packs and the number of strings. The total capacity again is the number of strings times the capacity of the battery. We have also added in additional options such as the cutoff of the state of charge. This means that the battery stops charging when it reaches 100% state of charge, and it stops discharging when it reaches 0% state of charge. And of course, these values are customizable. We will also utilize a battery management system that allows the user to define the control bus voltage as well as the characteristics of the BMS, such as the ability to charge the battery above a certain voltage range or discharge the battery when below a certain voltage range. You can also set the BMS to operate based on operating generation, which once again observes the power flow in a particular branch, such as a cable or a line or a transformer, to make a decision whether to charge or discharge the battery. Let's use the ETAP scenario wizard to run a couple of DC load flow cases. In these cases, we will observe what happens when the PV array power is increased from 10% irradiance to 40% irradiance, all the way up to 100% irradiance.
and observe the effect on the battery charge and discharge, as well as the contribution from the battery rectifier or the battery charger. First up is the case of 10% irradiance. We can observe the current and the voltage as well as the contribution from the battery, which is trying to compensate for the reduced power output from the PV array. We can also see contribution coming in from the rectifier into the DC system. The next case we will run is 40% irradiance. Here we can observe that the PV array power increases more than double its value. The voltage improves, and we can see that based on the BMS setting, the battery is no longer discharging and the power is purely compensated based on the contribution between the battery rectifier as well as the PV array. And finally, once we reach 100% irradiance in our system, and let's say that's in the afternoon, the PV array is generating majority of the power. The voltages are higher than the nominal values, and we can see that the battery is actually charging and absorbing the power, and there is no contribution coming from the battery rectifier. So once again, in summary, we can observe the behavior of the PV array, the battery, and the rectifier based on different irradiance levels of the PV panel and how they affect each other as you go from 10% to 40% to 100% irradiance. Next, let's go ahead and run DC short circuit. For DC short circuit, the typical approach is to run DC short circuit analysis and observe the fault current at various locations or buses or nodes in the system in order to size protective devices such as circuit breakers and fuses. This is typically done on worst case basis since we are sizing the equipment. However, there may be situations such as running arc flash calculations where you may want to vary the state of charge of the battery. We have already gone ahead and entered some state of charge inside our battery that varies from 50, 100, and 25%. So we can go ahead into our short circuit study case and set up the battery to use variable state of charge. The first state of charge that we would like to use is normal, where the state of charge is 100%. And we can observe that based on that state of charge, the contribution from the battery is 8.7 kiloamps. If we set the state of charge to 50%, we can observe that the fault current contribution changes to a lower number, which makes logical sense. And this is based on the battery model and the parametric model that we've previously defined. Similarly, if we go ahead and change our state of charge to a lower number, which is 25%, once again we can see our short circuit contribution is reduced. And based on this behavior, you can observe what would happen to the clearing times of protected devices. They would essentially tend to increase, increasing the I squared T and therefore the damage curve, particularly for DC arc flash cases. Therefore, the ability to model and simulate variable state of charge in DC short circuit is a very critical and important feature. Once we are done with DC short circuit calculations, we can also run a DC arc flash simulation. To do so, simply switch over to the DC arc flash mode and select the bus that you would like to fault for the simulation. You can simply right click to fault or unfault a bus, or utilize a study case to do the same. DC arc flash is a single click operation. It calculates the short circuit contributions through various sources in the circuit and utilizes the characteristic curves or the protection characteristics for fuses, breakers, and so on to determine the clearing time of the arcing current. So let's go ahead and run our DC arc flash simulation and observe the incident energy as well as the fault clearing time. Notice that the incident energy is 0.182 and the clearing time is 0.01 seconds. You will also observe that the short circuit current from battery 4 is less than what we observe from DC short circuit, because what we are showing here is in fact the arcing current and not the bolted fault or zero impedance fault current. We can then go ahead and follow the same steps and change our state of charge from 25% to 50% and observe how these numbers are changing. We can see that the incident energy increases slightly and the fault clearing time remains the same. And once we reach a value of 100% state of charge, we can also observe that the incident energy increases while the fault clearing time remains the same. And this is because as the state of charge is increasing, the fault current or the arcing current is increasing while the clearing time remains the same for this protected device. Therefore, the maximum impact to the incident energy is due to the increase of fault current and not due to the time delays created by the characteristic curve of the fuse. So therefore, we can observe what happens at different state of charges for the batteries in the system and how they interact and affect each other, and finally how they affect the arc flash boundary, the PPE requirement, as well as the incident energy. Let's switch our attention now to the interaction between the AC and the DC system. So far we've run DC load flow, DC short circuit, and DC arc flash. And our focus has been primarily on the DC system, which is again shown in this blue color. But we have a complete AC network connected upstream. This AC network is essentially a simple IEEE 13 bus network. So let's see what happens when we run our AC simulations and how does that differ with running a pure DC computation. ETAP unbalanced load flow in fact is a unified load flow that allows you to run AC and DC systems together. For those of you who are using unbalanced load flow, are running calculations primarily on the AC system, where you can observe the per phase values of voltage, current, as well as the neutral current and other parameters. When this unbalanced load flow is combined with the power of the DC system or the DC network, we are essentially running a unified load flow, where ETAP essentially solves unbalanced power flow on the AC network combined with the DC network simultaneously. These calculations are run together at the same time and not iteratively between the AC and DC network. So once again, when we go ahead and run our unified power flow, we can observe what happens when we have an AC and DC system that are interconnected together. We're now beginning to see what would happen when the DC network is connected to the AC side and what is now the complete picture or the power flow between these two systems. Let's go ahead and run a couple of cases using this unified load flow where we can see the interaction between the AC and DC system as we vary loading on the DC side. The first case, we will essentially leave the load as is and run our unified power flow calculation. Based on this simulation, we can observe that the PV array power is delivering energy into the DC load and also delivering power through the battery rectifier into the AC network. This essentially shows the behavior of this rectifier as a bidirectional converter. In order to set up this rectifier as a bidirectional converter, you also need to set up a regulation curve. ETAP includes a rectifier library where you can enter the manufacturer characteristics of the rectifier, such as its relationship of the voltage with respect to the output current. You can also define the rectifier as controlled or uncontrolled. This will allow some regulation on the rectifier input and output terminals depending upon the flow of power. In this case, we are using an uncontrolled rectifier, which implies that as the output current demand increases, the output voltage at the rectifier also starts reducing, and therefore it is an uncontrolled rectifier. In this case, we can observe that majority of the PV array power is being delivered through the rectifier into the AC network, and the battery is not charging nor discharging based on the BMS settings. We can then simply switch over to another case where we increase the DC load in our network. When the DC load is increased, you can see the power change on the DC load, and this battery is now delivering additional power into the DC circuit, and the power contribution or the injection into the AC network is reduced. And finally, we can switch over to another case where we are eliminating this DC load completely while we remain or keep the PV array power constant. In this case, we can see the PV array power once again is being delivered to the AC side, and additional current is being absorbed by the battery. So therefore, the BMS modes work in all the DC computations as well as unified power flow simulations. Since we've looked at DC systems and unified load flow, the next logical step is to look at time domain load flow. Time domain load flow is particularly useful when we are varying loading or generation as function of time, and we are including controls such as tap changers, switch capacitor banks, and of course battery management systems as well. Our system includes a number of PV arrays as well as a complex network of generators and loads, and it also includes a combination of a DC network along with the AC system integrated together. Time domain load flow also allows you to define various events. Inside the events, you can also define a particular event that may occur at a given period in time and define the action associated with that event, such as opening or closing switches or even adjusting the voltages of sources as well as adjusting the loading as a function of time. Each component, such as a generator, PV array, or source, can have a time profile associated with it, and you can observe that in this case I'm using an Excel file to provide irradiance information for this particular PV panel. We will vary the irradiance on the PV panels as function of time using our external data and observe what happens to the entire system power flow as a result of that. Once the time domain load flow simulation is completed, you can observe the results of the AC and DC system together at the same time. We can see the unbalanced power flow per phase and the voltages on the AC network, and we can also see the DC side calculation at the same time. These are all tied together using the time domain time slider that allows us to move the results or vary the results as function of time and observe the power flows and the voltages in the network by just simply moving this time slider. You can also see the results using plots, which we will see in a little bit. In the beginning, you can observe that the state of charge of the battery is 50%. As you move the time slider, the program automatically determines what the result is at that moment in time that you have selected and provides the new state of charge, the new voltages and the flows in the system at that day and at that time. What's important to understand for time domain load flow is you're not limited to an hourly step or a minute step. If you use external data, you can in fact even put smaller steps that may go into a second time frame, and you can run computations for a whole day, an hour, a week, a month, a year, or even multiple years, depending upon the target and the objective. So let's look at some of these results in terms of plot. First of all, we can see what happens to the PV arrays that we are varying in our system. We can see the power, current, irradiance, and temperature, and see what those plots look like. This essentially shows us a daily PV array profile that shows how the PV array power is increasing and decreasing over sunrise and sunset. And we have some cases during the day where the PV array power production is not optimal, and we also have cases where we have potentially cloud covers that reduces the PV array power temporarily. So let's go ahead and see the effect that this has on our battery, and we can see the voltage, current, and state of charge energy. Let's start by looking at voltage and current of the battery and the effect that it has, the PV array profile has on the battery itself. And we can see that as the PV array production changes, the battery voltage and current varies at the same time. And this is controlled based on the BMS operation. We can also observe the battery characteristics in terms of the power generation and state of charge energy. And that provides us a stepped response of state of charge energy as this battery is slowly being charged. And it also has moments where the battery is no longer being charged in order to deliver power into the system. Now that we've looked at the effect of running time domain load flow and the interaction of the BMS, or the battery energy storage system, with a time domain load flow, it therefore of course has applications for renewable power plants as well as microgrid systems in order to perform a time varying power flow simulation. ETAP can also be used for railway traction power system simulation. eTrack software allows the user to model the AC and DC railway traction systems, including the transmission system, and solve a unified power flow, which is unbalanced AC and DC combined simultaneous power flow with a multi-physics simulation. So this includes the various effects of resistance on the traction motor, such as bearing resistance, rolling resistance, wind resistance, elevation, curvature or bends in the railway track, its effect on the mechanical energy demand on the traction motor, which is then converted over to the electrical consumption and the voltage drops on the AC side as well as the DC side of the system. And this is run as a continuous function of time. So eTrax allows you to solve the entire AC and DC traction system as a function of time, including the railway timetable and its optimization, and you visualize the results on a single line diagram as well as a geospatial diagram. To this, we have essentially added the ability to include wayside energy storage or battery energy storage. So let's take a quick example of railway traction systems with battery energy storage. In the eTrack simulation, we can see that the power flows are visualized on the one line diagram, as well as the movement of the train is shown on the GIS side. Using the time slider, you can press play and allow the program to start playing the timetable and the results of the timetable from a given time to an end time. And the playback rate can be varied, and the playback location can be varied as well. You can then also observe what the battery is doing as the power flow is changing as function of time. In this case, we can observe that the battery is actually charging current, while we have some power flowing from the AC system through the rectifier into the DC network. And at some moments in time, we can see that the battery essentially stops charging, and this may be the case where a train is essentially accelerating in the system where you don't want the battery to charge. By adjusting the BMS and the state of charge and the BMS settings, you can fine-tune the battery energy storage such that you are charging and discharging at appropriate moments and essentially conserving energy. So therefore, when the train is accelerating, you can set up the battery to discharge and periodically supply additional power and eliminate the AC demand in the system. And when the train is braking or is capable of regenerative braking, you can then absorb that energy and charge the battery at the same time. So therefore, we can simply move our time sliders and observe what happens when we have a number of trains moving through the system at the same time. And you can see that when you have many trains in this corridor, the battery is now essentially discharging and providing that additional power support and voltage support as needed for the DC system. So therefore, in summary, once again, you can use eTrax to solve an AC and DC unified traction system. It is a multi-physics simulation, so that includes the mechanical movement and the behavior or the nature of the trains. It includes a timetable simulation, as well as the ability to solve power as function of time. And combined with battery energy storage, you can then simulate and see the effect of adding batteries and sizing the batteries such that you're able to conserve power and reduce demand from the AC side. You can also plot all of this information just like time domain load flow as function of time and observe the behavior of the battery voltage and current as it goes through various transitions of charging, no charge, and discharge in the system, and how it's able to maintain the terminal voltage at the battery terminals or the substation terminal buses as well. So far, we've been looking at steady state analysis such as power flow, unified power flow, and DC short circuit. Let's turn our attention now to the dynamic side and observe a few examples related to dynamic RMS. In ETAP, you can actually model the dynamics of battery energy storage systems together with their controller using UDM. ETAP already includes UDM models for plant level control and also includes WECC battery energy storage models. So let's take an example where we've utilized the WECC battery energy storage models along with the plant level control and run a few simulations and observe the transient behavior of battery energy storage systems in ETAP software. In ETAP, you can define the dynamic models for various components such as generators, loads, wind turbines, battery energy storage systems, inverters, and so on. These dynamics essentially include control systems, which can be defined using the UDM editor. The UDM, or User-Defined Dynamic Model Editor, is a graphic logic editor that allows you to model the transfer functions of various control systems. Once you have built the transfer function, you can also compile the transfer function and create a black box model of this control system diagram. For situations where the control blocks may be insufficient, you can also add a script block and use C# syntax to define any kind of logic that cannot be defined using these standard control blocks. Using UDM, we can build the complete battery energy storage system transfer function that not only includes the plant level controller, but it also includes the state of charge logic. So in this instance, we can see that the state of charge logic has been already defined. It includes certain variables such as the maximum minimum state of charge, as well as some initial state of charge. Its output is then driven into an electrical controller, which is also defined, that includes various modes of operation such as voltage control, power factor control, reactive power control, and so on. So combining the transfer functions from UDM and the dynamics from various elements, we can run a network simulation in transient stability and solve the power flow at different steps in time. Just like with time domain load flow and E-tracks, transient stability also provides us with a action slider as well as a time slider that allows us to move the simulation as function of time and observe various user-defined actions as well as the program-related actions or automated actions such as relay trips in this event list. So let's set our simulation back to time equals 0 and observe our one-line diagram. We can see that the yellowish color corresponds to slight under voltage in the system, whereas the blue color corresponds to slight over voltage in the network around our nominal value of 100%. We can then move our action slider to the next action in our sequence, where we're defining circuit breaker 6 is open at time equals 10 seconds. This is corresponding to some kind of load rejection or load shed in the system. And at that moment in time, we can observe a significant overvoltage in the network as anticipated because we have lost load in the circuit, and our control system must therefore compensate for this overvoltage condition. We can then move to the end of our simulation and see the final result, and we can see that the voltages have recovered and the blue areas shown with the color contouring have essentially dissipated on our one-line diagram. We can simply turn the contouring on and off by using the contour button. You can also use the plot view to observe plots for various other components in the system, such as the generator, and observe all the different parameters of the unit as it goes through this disturbance. And you can see that the relative angle change is very minimal and the generator speed fluctuation is also very minimal, but nonetheless you can see in detail the transient nature of the change in generator speed as that load is dropped, and then the compensation is provided by the battery energy storage system. Depending upon the controller, you can set up the battery to either discharge, charge, or automatically charge and discharge. And this is purely a function of the control system itself. You can also observe other things in the circuit, like the bus voltage and frequency and so on and so forth. And once again, observe the disturbances or transients at any point in the system. Now that we have included a UDM model for battery energy storage based on WECC, and observe what happens when we apply an event and see the effect or the disturbance on our network. This is a RMS simulation, so therefore we can now turn our attention over to dynamic or EMT simulation. For EMT simulation, ETAP works hand in hand with PSCAD, where we can essentially combine the best of both worlds and achieve a dynamic EMT calculation for our power electronic models while solving RMS values for our complete network simulation. This hybrid co-simulation capability allows the user to model fairly large networks in ETAP, yet include all the details of the power electronics as part of the simulation and observe the entire network response without losing any fidelity of their network models. So let's take an example of a co-simulation between ETAP and PSCAD, especially for battery energy storage systems. This is a simple example showing a generator, a load, and an EMT load connected to our co-simulation bus. This EMT load is representing a battery, a DC to DC converter or a buck boost converter, an inverter, as well as a transformer connected to the BESS station. The boundary is essentially the BES station that corresponds to the co-simulation bus. So therefore, the section of the system that you see in green is represented in PSCAD in full fidelity. This system will be solved in microsecond step, while ETAP is solving the entire network in 0.1 millisecond step. When the co-simulation process is begun, you can just simply run ETAP transient stability, and when ETAP is essentially connected to PSCAD, you can go ahead and click OK and allow ETAP to run the transient stability calculations while PSCAD is running its EMT-based simulations. You can also observe on both sides what is the calculation or the simulation response from the combined or co-simulated approach. And in this case, you can observe what the ETAP interaction is with the PSCAD along with the PSCAD EMT time domain simulations as well. You can of course utilize the capability to zoom the charts and observe that at this moment between 2 to 3 seconds there was essentially a disturbance that was created on the ETAP side, and that disturbance was essentially a fault at t equals 2 seconds that occurred at this particular bus in time, and the fault was cleared at 2.5 seconds. So we can observe that in EMT as instantaneous values, and you can also observe the interaction with ETAP on the RMS side. You can also visualize the results, and in this case we can go ahead and plot our EMT load and observe megawatt, megavar current and voltage as a combination. And this essentially shows us the exact same response as we saw on the PSCAD side, which is the RMS response from ETAP, while we were observing the PSCAD EMT calculations within PSCAD environment itself. We can also go ahead and plot other variables such as the bus voltages, and we can close these plots out so you can see the bus voltage and power in more detail. And once again, this shows us the effect of our disturbance on the boundary bus or the co-simulation bus. So with this technique of co-simulation, you can use ETAP transient stability co-simulating with PSCAD, where you can solve the instantaneous values per phase in microsecond step, include them in the ETAP transient stability simulation in 0.1 millisecond step. So you land up including the entire power electronics behavior as part of the complete network simulation. And the events can be introduced in ETAP as usual. The relay automatic actions occur in ETAP as usual. So you are left with an environment that you're comfortable with and used to, and yet include all the details of PSCAD dynamic modeling or power electronics modeling within the ETAP environment. So again, in this case, we utilized a battery energy storage model, which can be built inside PSCAD along with the power electronics of the DC to DC converter and the inverter, and solved it together with ETAP in a co-simulation environment. As I mentioned earlier, the BESS models are not only used for design, such as the steady state, short circuits, time domain, dynamic RMS, or dynamic EMT, but they can be also transitioned over to real time. So BESS monitoring and control is part of ETAP microgrid and nanogrid solutions, where we utilize a microgrid controller or a nanogrid controller at each site to essentially bring in data from the power grid, the energy storage system, any diesel generators. We bring in generation loading from any other connected sites that may be part of the same subsystem, or they might be related to this particular site. We also bring in information from the loads such as the AC, DC, and critical loads. The controller includes the battery charger model that we have designed and developed in ETAP, and it is included as part of the microgrid controller. And using the controller logic, we continuously process at every step the state of charge, the load demand, the grid availability, and based on that we predict the battery state of charge. We predict the time to minimum state of charge, that is when the battery is going to be fully discharged, and then we send notifications accordingly to the network operating center or the ETAP SCADA PMS that is situated at the network operating center or the control room. The controller is also able to send out control actions or alternative actions, such as switching to an alternate source in case the battery state of charge reaches minimum value, or it can also shed loads or non-essential loads in multiple stages to preserve the state of charge of the battery and extend the battery life as long as possible. So this finds applications once again in microgrids and nanogrids that may range anywhere from a few 100 kilowatts all the way into the megawatt range. In conclusion, ETAP supports steady state and dynamic RMS or EMT modeling of battery energy storage systems. We have observed that through examples for DC load flow, DC short circuit, DC arc flash, time domain load flow, E-tracks or train simulation, transient stability, as well as co-simulation with PSCAD. BESS is an enhancement to your existing battery element. The only thing BESS simulation requires is license of relevant calculation engines that will be used along with the battery model. So therefore, if you have an up-to-date maintenance of ETAP, you automatically get the advantage of having lithium-ion batteries and the BMS system as part of your ETAP upgrade. You can utilize unified load flow and UDM to unlock detailed simulations and time domain simulations of battery charging and discharging behaviors. And you can use this kind of behavior for microgrid, railway, renewable, distribution, and other applications that may include utility scale energy storage or transmission projects as well. Thank you very much for attending this webinar, and we look forward to seeing you in our upcoming webinars related to energy storage and microgrid.